This lesson is a continuation of what was covered in class today, April 2nd, 2013, where we were studying optimization problems using calculus. So when you are working with problem solving where the focus is optimization, here are a few key points that are important to remember. So firstly, you are determining or trying to determine the maximum or a minimum value of a particular quantity. And as was shown, we had studied a couple of different examples, one that involved volume, and then another one which involved minimizing costs. So the one we're going to look at today involves a little bit of geometry. There isn't a specific context, but it could be mapped into a number of different domains, and that one might find of interest. The second point is that we develop the models, so models, that is to say, formulas, equations, are developed using information in the problem. Okay, so it's always a good idea to mark out what you have and what you're trying to find. And definitely draw a diagram where possible. So the numerical solution represents the extreme value. Okay, so we are looking for extreme values. So with that being said, we can see how first derivative of a function can be of value to us. So if we're looking for a procedure, a method, or an algorithm for solving these kinds of problems, number one, understand the problem, identify the quantities that are able to change. So just what exactly is x going to be in the context of the problem? And then to determine a function.
Could Chris Sainsbury, Sam Petersma, and Shannon Ball please come to guidance? Chris Sainsbury, Sam Petersma, and Shannon Ball to the guidance area.
In one variable that represents what you're trying to optimize. Whenever possible, sketch a diagram, putting labels in accordingly. Number three, and this is really important, is to determine the domain of the function that you're trying to optimize. Because as you have seen and will see, certain values or solutions lie beyond the domain of the function and hence have to be rejected. Number four, use the methods of finding first derivatives in terms of finding your absolute maxes or mins, and then answer the question. So here's a particular problem that's going to combine geometry with calculus. So this is a particular type of question that you might see down the road. You might see different topics that stem off of this particular concept. So we're trying to find the dimensions of the largest rectangle that can be placed inside, or that is inscribed, just so it touches the perimeter of an ellipse. Okay, so an ellipse is much like kind of a relative to the circle and also to the hyperbola and parabola. They're all what we call sections or cross sections or certain sections of a cone or a right circular cone. We don't study that in this course, but you can definitely look these up online or in a reference book. So if we strictly focus on the rectangle that's there, what I do want you to take note of is the fact that from the origin and sweeping to the right to a particular point, which we have here, I'll just highlight that in green. Okay, that point there, we're going to denote that as x comma f at x, and just remember that f at x is y. Okay. Something else that I also need you to recognize is that if we move in the same direction, but towards the left, sweeping this way, we do see that the length of the rectangle, direction plus and minus not really significant here, but the length of that particular rectangle would be 2x. Okay. Now, if we are concerned about the width, well, the width is dependent on y, or dependent upon f at x. So here we have a distance of f at x. Here we have another distance of f at x. So we can kind of appreciate that the width and the designation of length and width are arbitrary. It doesn't matter which one is which. It all depends on your perspective. This would be 2y, or equivalent to 2 times f at x. Okay? So in order for us to determine an area function, right? So area would be equal to length width, in this case, 2x by 2, 2y. Okay? The problem with our function lies in the fact that it is being defined in terms of two variables. So we have, whoops, that was not my intention to shift that down, but rather was to highlight. Let's try that again. Being defined in terms of two functions. We have x and we have y.
Could Jordy Deacon, Chris Sainsbury, Sam Duzma, and Shannon Ball please come to guidance? Jordy Deacon, Chris Sainsbury, Sam Duzma, and Shannon Ball to the guidance area, please.
So in order for us to develop a function that can be maximized, because remember, we are trying to find the dimensions of the largest rectangle, the rectangle that fits just nicely inside of this ellipse. We need to figure out an expression for y, right? Because typically our functions are defined in terms of x. So we really do need to figure out this expression here. Like, what's going to go in there? Okay, here's what we're after. Because if we can figure that out, and it goes here. Okay, and then we can find the first derivative, get the critical value or values, compare that back to the domain, and then we should be good to go. Okay, so let's go about figuring that out. So we're going to determine the y from this equation here. Okay, now in order for us to begin working with the equation of an ellipse, or in particular this, what we call a conic section, so conic from the word or cone, and the section we're looking at here is the ellipse. So in order for us to do that, we need to get the right-hand side equal to 1. So the general form for a conic section, that is the equation, is to have one side equal to 1. Well, what that means is that we're going to have to divide each and every term by 16. Okay, so then we'll arrive at the following: x squared over 16 plus y squared over 4. Okay. Another thing we can do moving forward, and this is kind of, this method is a little separate from what we could do directly in terms of getting the y value, and I only bring this part in because we don't cover the conic sections further in high school, so it might be good to get a little background on this. So what we're going to do is we're going to rewrite the denominators as perfect squares. So this will be 4 squared and this will be 2 squared. What the 4 and the 2 represent, okay? So if we go up to our diagram, notice that the y value here is 2. Okay? Notice that that is equal, oops, sorry, not that value, folks. My apologies. Let's move that up a little bit according to our scale. There's the 2. And then the 4 would be right out here. Okay? So what that means, okay, is that if we were to take the 4 and map it to the diagram, we would have the length or could calculate the length of this horizontal axis. That is the width of the ellipse. Okay, so there are particular terminologies associated with that. If memory serves me correctly, they're both the transverse and the conjugate axes, but the 4 and the 2, right? 2 by 4 equals 8, right? So we have the width of the ellipse, and then here 2 2's making the 4, where we would have the height length of the ellipse. Okay, but that is kind of separate to what we really need to accomplish. What we do want to do is to take the function and we'd like to solve for y. Okay, so let's isolate the y term. And then let's solve for y. So if we take the square root of both sides, of plus or minus, we can take the root of 4. Okay, so what we've determined is that the y coordinate of this point up here, okay, let's go back and fill that in, that this thing here, I'm going to erase this and actually write it in place, would be the root of 16 minus x squared all over 2. That is the positive, right? So the positive meaning the top half of the ellipse, negative the bottom. So let's just indicate that here. So positive root would be the top half. So negative being the bottom half of the ellipse. So we're approaching about 12 minutes in terms of this video. What we'll do is we'll split it into 2 parts. Okay, so part 1, part 2. So let's finish this off here. Let's set up our function. So we now have a value for y in terms of x. So why don't we develop or determine the area function? Let's call it a at x, where x is going to represent, or actually 2x, but in this case x is going to help us to determine the dimensions of the rectangle. So a at x is going to be equal to, what did we say here, folks? We had length by width of the rectangle was 2x, 2y. So we have 2x, and then 2y is going to end up being 2 times. And we're going to stick with the top half. Let's just go positive square root. So root of 16 minus x squared. Okay. So it will then be our job in the next video to determine critical values. So we will determine a prime at x. We will then set a prime at x to 0. We will solve. Okay. We will then compare x values to the domain, see which ones are or are not acceptable, and then we will determine or calculate the dimensions. Okay, so just to repeat here, let's write down a prime at x, let's write a at x, and then in the next video we can start up by finding the first derivative. And I feel like we're missing one thing, and that is, yes, it was divided by 2. Same thing back here. Let me correct that page. Perfect. Okay, and while we're on the topic, I guess we might as well simplify. These 2's will cancel, and thus a at x is going to be 2x multiplied by the root of 16 minus x squared. Okay, and I guess while we're on the topic, before we shut this video down, if we look back at the values that would be acceptable for x, notice that in terms of the rectangle being inside of the ellipse, okay, the greatest value that x will take on is 4. The least value, although not equal to it, would have to be 0. Okay, so as far as domain is concerned, what we really should be looking at are these values here. Now, can it be 4? Well, no. Reason being, substitute in 4, and you're going to have a 0 for the area. The same thing occurs if you sub in 0 here, you're going to have 0 for the value of the area. So that just does not make sense. So we're going to take or restrict our values between 0 and 4. So if our critical values lie beyond that, then no solution. But we should expect one of the values to lie within that range.